Hi all, I'm Poorni, working as an assistant professor in the Department of Industrial Biotechnology, and I'm going to handle the subject called Bioprocess Engineering, and I am taking the topic called Substrate Utilization and Production Kinetics Rate. So, as we all know that the bioprocess is said to be the heart of the fermentation process, in which your microorganisms utilizes all the substrate for their product conversion. So, for your anything of your bioprocess, when we talk about the microorganisms utilizes the substrate, whichever we are giving as a nutrients as a supplement for your product formation. Okay, so here when we are going to inoculate the substrate, the organisms will utilize those substrate so that the rate of the organisms will be gradually increases since it is involved in the formation of a product. So here when we talk about in the case of any fermentation process, if you take, so let us see about the batch fermentation process. So here in this case there are 4 different phases in the stage of a cell cycle, growth cycle of a microorganism. So the first is said to be the lag phase. So when we talk about a lag phase, this is said to be the lag phase. So here when we are going to give the nutrients as a supplement for the microorganisms during the inoculation in the case of a bioprocess or a fermentation process, the nutrients whatever we are giving, that will be utilized by the microorganisms, which means that this utilizes as your substrate getting utilized, or we can tell the microorganism has started to uptake or adjust to the newer environment for utilizing the substrate for a product conversion. So once a nutrient has been uptake or adapted to the by the microorganisms, it will be taken into the next phase called a log phase or an exponential phase. So when we talk about a log phase or an exponential phase, here there will be of a cell which will start to divide or increase in the number of your cell or in a cell mass. So when once all the nutrients has been taken up by the microorganisms for their growth, the cell starts to divide in the case of this log phase. And once it has been finished, it will be taken to the next phase called a stationary phase. So in this case of a stationary phase, the product will be starts to form. So that product can be of either a primary or a secondary or whatever it might be. Okay, so here in this case, in the stationary phase, there will be a product formation by as your this stationary phase, it indicates there is no further growth of the cell, which means that the growth of a cell has been attained entirely for the newer product formation. So once a newer product has been formed, it will be taken to your next phase, that is said to be the decline phase, which means, or we can also call it as a death phase, which means there won't be of any organism which will be involved in the formation of a product. Okay, which means that the cell also stops growing, so the product also will be stopped, so that it will be, we are called that as a death phase or a decline phase. So the next one, when we talk about your exponential phase, whatever the cell is being phase which has been grown in the case of your log phase is directly proportional to the concentration of a biomass, that is a cell concentration you can take. So that can be written as dx by dt is directly proportional to x, which means that in order to remove this x, a constant term, we are introducing a constant term called a nu, that is said to be the specific growth rate of your microorganisms which has been imparted for a particular product formation in the terms of your cell or a biomass. Okay, so the dx by dt is directly proportional to the x, which is can be written to remove this alpha constant term. So we call that dx by dt is equal to mu x. So the x represents the concentration of a biomass or a cell concentration, and mu represents the specific growth rate, and x represents the biomass, and t represents at a particular time how much amount of the product has been formed by utilizing the substrate for the product. So here when we are going to integrate the equation in which the t varies from 0 to the final time at the end of the process of a fermentation. So that is at t. which means that this from this time to this time, the concentration difference can be written as or varies from x0 to xt. So from t0 to t, in which your x will be varies from x0 to xt. So when we are integrating the first equation of dx by dt is equal to mu x, by integrating that equation, we'll get the equation as xt is equal to x0 into e to the power of mu t, in which x0 represents the original biomass concentration at the time t is equal to 0, and xt represents at the end of the fermentation process what is the biomass concentration at the final time t is equal to t, and mu represents the specific growth rate of a microorganism. So here in this case, when you talk taking a ln on both the side, the ln of xt is equal to ln of x0. By removing this exponential term, as we are introducing the ln, so it becomes a plus into mu t. So xt is equal to ln of xt is equal to ln of x0 plus mu t. So here this equation is said to be in the form of your linear form, which can be written as a y is equal to mx plus c. So here, by rearranging this equation, your ln of xt on a y-axis and on your x-axis, we are going to take it as a t. So that is your y is equal to mx plus c. So the y is said to be the ln of xt, which is taking on an x-axis, which is plotting against the time t on a y-axis, and it will give a slope in a straight line, and with the slope which will give you as a mu, that is said to be the slope, that is a m. So the slope value will give you the nu, that is a specific growth rate of a particular organism which imparts in the product formation. Whereas the x0, which will be given from an intercept value that we can be able to find out from the intercept. So here when we are going to plot a graph between a biomass concentration of logarithmic on an y-axis and against your time t on an x-axis, that will lead a straight line in which the slope will be given the form of a nu, that is a specific growth rate of a microorganisms. Always the specific growth rate of a microorganisms can be denoted as a nu, and the unit will be of a time inverse. Okay, so here when we talk about a nu, this can also be written as a maximum specific growth rate also, which means that since in an exponential phase all the nutrients has been taken up by the microorganism, so the maximum amount of the product has been formed. So the nu can be written as a nu max. So the equation can be written as xt is equal to x0 into e to the power of nu max into t. So as we all know, that is the first phase, which is said to be the lag phase. There are no cell division or a cell mass has been increased because your that why it has been lagging in the case of a cell division or a cell number, which means that the environment has been adapted newly by the microorganisms for their uptake to get adapted, so that it will be involved in the formation of a product by utilizing the substrate. So the growth of organisms will be always equivalent to 0. This is in the case of a lag phase. So the next one is an exponential phase. So as in the exponential phase, the nutrients, whatever it has been there, it starts to uptake, so that it will starts to divide in a case of a number of a cell. So which means that how the bacteria will be divided, it will be in a doubling in a size. So the growth can be written as a doubling of a size, that is equal to 2 to the power of n. So which means that the final x will be the doubling of an initial cell concentration. So here in this diagram, this is your parental cell that you are inoculating as an inoculated culture. So when it has started to adapt in the case of the lag phase, it will start to take up the nutrients. So finally it will be divided into a n number of your cells. So here, which means that this acting as a parental cell for dividing the cell into the 2 numbers. So here, which means that your 1 cell is getting divided into the 2 cells. So which means that this is said to be the xt, so that which is nothing but your doubling of your initial cell concentration. That's why we have your x as your 2 to the power of your x naught. So when we are substituting this x is equal to 2 to the power of n into x naught, here if you are substituting, so that will become your value as your TD is equal to ln of 2 divided by mu. From this, the specific growth rate of a microorganisms can be identified or it can be derived. So it derives the final form of a doubling time. The TD represents a doubling time, which can be written as a ln of 2 divided by mu, or the mu can be written as ln of 2 divided by doubling time TD. So how we can measure the growth rate during your exponential phase? So in the case of your exponential phase, when we talk about, there will be a product formation that will be occurring in a station, which means that in the case of an exponential phase, if the nutrients all will be occupied or get taken up by the microorganisms for the product formation. So which means that your dx by dt is equal to nu into x. So this can be written in the linear form of an equation, y is equal to ms plus c, which will give you the straight line that will give you the slope, which will give you slope as a new value and your intercept as a x naught, right? So the next stationary phase, when you talk about moving to the station, so here what happens in the stationary phase, the nutrients will become limiting, which means that it has been already uptaken by the microorganisms entirely, so that the product is started to form. So here what happens in the stationary phase, there will be a formation of a product as well as your undesired product in the form of a byproduct also will be there. That's why we have say the nutrients becomes limiting, and thereby the toxic waste products gets accumulated. So there are no growth in the case of a stationary phase, which means that only the product formation after the growth and getting into the stationary phase. So the growth is equal to the death. So the dx by dt is equivalent to 0. And the last, what is the last phase? That is a death phase. So here in the death phase, there is a no growth phase, though. So the growth phase will be started to be a negligible one, which means that the nutrient has been entirely taken up by the microorganism as a substrate utilization for the product formation. So the dx by dt can be written as the minus of kd into x, which means that this kd is said to be the death kinetics of a microorganism. So this can also be written in terms of your number of a cell. So the dn by dt is equal to minus of kd by n. So that is based on a number of a cell. This is based on a growth of the cell, how it can be written. That is a cell mass. If it is of a number of a cell, it can be written as a dn by dt is equal to minus kd into n. So the next, how this substrate is being utilized for the growth of the microorganisms, we will see. So when we talk about a substrate concentration of the microorganism, this has been entirely dependent on the nutrients what we are giving as a substrate. Why we are giving? For their particular microorganisms has to be utilized, though, so it has been growing and it is resulted in the formation of a product. So when the product will be over, this product will be occurred only in the case of a stationary phase. So which means that the cessation of the growth, which means that that is said to be the stopping of your growth phase. When this growth is being stopped, the growth will be stopped when the nutrient has been entirely utilized by the microorganism. So the cessation of the growth, the stoppage of the growth is due to the depletion of the nutrients that has been provided in the medium as the substrate. And also not only it depends upon the nutrients as the substrate we are giving for the microorganism, which means that the toxic also gets accumulated. That is the products and the undesired product as a byproduct also gets accumulated in the stationary phase. So your microorganism must stop growth after the product has been formed. So that's why we say when the substrate has been limited and the toxic has been limited, the microorganism growth has been entirely stopped. So how this can be described in this figure we will see. So here the initial substrate concentration. So when we talk about the initial substrate concentration on an x-axis and biomass concentration on a y-axis. So when you talk about a initial substrate concentration, so here in this case, when your substrate concentration is more, here in this case, when your substrate concentration is initial, there is a no biomass has been occurred. Which means that once the concentration has been started to utilize by the microorganism, it started to give your biomass in an increase, gradually increase as your substrate has been increased or utilized by the microorganism. So once it has been attained or reached the end of your lag phase, it starts to attain into the log phase, so that all the organisms will be starts to divide by their after the growth and a division in a mass or in a number. So once it has been occurred, once the substrate has been stopped or utilized by the microorganism, so it reaches the stationary phase. So that's why we have a flat horizontal line in this plot, which means that the substrate has been entirely utilized by the microorganisms for the biomass formation. So here, this zone of A to the B represents as the increase in the substrate concentration. Therefore, the biomass concentrations can be increased. So which can be given as X is equal to Y into SR minus of S. So which means that the X represents your biomass concentration and Y represents the yield. So how much amount of the product has been yield based on a substrate. So when you talk about the substrate, here we are giving the initial substrate in a particular value that is in a maximum one that has been started to utilize with the microorganisms, and final when we are taking the substrate concentration will be of a minimum or it will be of a zero. So that's why it has been given as a difference of a SR minus S. So what is the SR? It is the initial substrate concentration which will be of maximum of about 100 or a 200 or 1000 it might be. And when we talk about the S, it is said to be the residual substrate concentration, which means that at the end of the fermentation process of a batch, the concentration of a substrate will be of a minimum or a negligible one. So this equation is used to predict the how much amount of the biomass has been produced by utilizing the substrate. So what is the biomass? It is can be defined as a product formation. So how this product has been formed? By utilizing the substrate. That is a nutrient. So X is equal to Y into SR minus of S. So here in this case, this graph also indicates that zone from A to the B, it is said to be a cessation of the growth, which means that the stopping of the growth will be there. And from the zone C to the D, which means that the substrate concentration gives directly proportional to the biomass as your substrate has been uptaken by the microorganisms for the toxic product formation. So the next one we'll see about the Monarch equation. So as we all clear that in the case of a batch fermentation, how the nutrient as the substrate has been utilized for the microorganism for the product formation, that from that equation, it is also known that we can calculate the specific growth rate. So here we are taking the specific growth rate estimation into the next higher level that has been prescribed by the scientist called Monarch. So we call that equation as a Monarch equation. And this Monarch equation is also used to predict what is the specific growth rate or a maximum specific growth rate by utilizing the substrate for a product formation. So here in this case, when you talk about your Monarch equation, the decrease in a growth rate or stoppage of a growth is due to the depletion of a substrate. Since all the organisms has been entirely utilized, all the supplements what we have been given as a raw material or the nutrients for the product formation. So which gives a relationship as your ln of x is equal to ln of x naught plus nu t, right? So here this equation can be represented to the next higher level that has been prescribed by the scientist called Monarch. So we call the equation as a Monarch equation. So when I talk about a Monarch equation, this Monarch scientists have taken a base equation from a Microscopy kinetics. So what do you mean by the Microscopy kinetics? First, people, you were aware of your enzyme substrate reaction. The enzyme substrate reaction kinetics, in which the substrate which will be reacting with the enzyme, or the enzyme is acting on a particular substrate to speed up of a reaction to give a particular product. So here in this case, the equation of a Microscopy can be given as V is equal to V max S divided by Km plus S. So here the V can be, so here in the Monarch equation from the Microscopy equation can be replaced as a nu, because we are detecting or determining the specific growth rate of a microorganisms by placing of a substrate for a product formation. So here in terms of a V, we are going to replace your nu. So the nu is equal to nu max S divided by Ks plus S. So this Ks represents your substrate utilization constant. So how much amount of the substrate has been utilized for your product formation. And nu max represents where your maximum concentration of your substrate in which the maximum amount of the product has been formed by the microorganisms action. That's why we call this as a nu max. So the nu is equal to nu max S divided by Ks plus S. And the S represents your substrate concentration. And here also always keep in mind that the specific growth rate of a microorganisms can be represented as nu, and always it has a unit of a time inverse. So here in this case, there is this concentration has been increased, the specific growth rate of a microorganism also increases. So that is how it has been given. So this zone of an A to B, which means that exponential phase in which the batch culture, where your substrate concentration is directly proportional to your nu, that is which gives a value of this region from this A to B, the value on this one from this intersection, it will give you the value of a nu. And this A to the C, which represents a deceleration or a death phase, as the substrate concentration has been limiting, which means that that is a no growth rate of a microorganism. So we cannot predict your nu as the product has been entirely formed in the case of a stationary phase. So which will not give you the value of a nu. So here we are going to see the two different conditions. So what is the concentration substrate influences in a batch culture? So when you talk about in the batch culture, there are three parameters that is helps to determine your substrate concentration in the case of a batch culture. The first one is the substrate concentration, the next one is the nu max, and the next one is the Ks. So this is how we do have your Monarch equation as nu is equal to nu max divided by Ks plus S into S. So here the specific growth rate is independent of your substrate concentration. Okay, which means that, so here we are going to take a reciprocal of this equation to make a linear form of an equation of a y is equal to mx plus c. Okay, so when we are deriving the equation, it will be having your y on your 1 by nu as a y, and on an x-axis we are going to plot a 1 by s. So when we are plotting a graph, it will give you the straight line with the intercept of on a y-axis of your 1 by nu max, and the slope value will give you the Ks by nu max. Okay. So here for your next condition, in the case of a continuous mode of an operation of a fermentation process. So here when we are going to talk about the continuous mode of an operation, whatever the amount we are deriving when the reaction is being carried out, we are going to give that amount of a reactant for equalizing the reaction process. So how much amount of the we are deriving as an outlet, we are going to make it as some amount as a inlet. So here in this case, it is said to be the continuous growth of a kinetics. So here when we talk about the actual rate, that's independent on a volumetric rate of a medium, so that we can have a new term in the case of a kinetics growth kinetics as a D is equal to F by V. So here the D represents the dilution rate, that which means that we are adding a substrate as a nutrients in a sum of a middle time for the reactions to be proceeded. So that in how much amount of a volume is denoted by the V. So here the D is equal to F by V. So in this, under a steady state conditions that we talk, the rate of the growth will be equivalent to the rate of the loss, which means that the dx by dt is equal to 0. So substituting the nu x. So what is the rate of the growth in the case of a reactor? That is a nu x. So the rate of a loss from the reactor is said to be the dx. That is the inlet minus of your outlet. So the inlet is said to be the nu x, and outlet is said to be the dx. That is the gaining minus of a losing. So here the nu x minus of dx is equal to dx by dt. So here in this case, the dx by dt is equal to 0 at a steady state condition. So the nu will be directly proportional to the d. So what is the value of getting as a mu in the case of continuous, which will be equivalent to the dilution rate of your continuous fermenter. So here when you talk about this thing, here we are going to make, so for this equation also we are going to make the Monarch equation in a linear form to find what is the nu and what is the specific growth rate and what is from the slope and what from the intercept, what we need to find it from a concentrate. So here we are going to make the Monarch equation of nu is equal to nu max S divided by Ks plus S. So as we all know, in the continuous continuous mode of an operation, the D is equivalent to the nu. So replacing the nu term as a D, so the D is equal to nu max SR divided by Ks plus SR. The SR is said to be the residual substrate concentration that has been left at the end of the process, that is a dilution rate. So by replacing this term, we will be having the equation of this form, which will be used to find what is the substrate that has been left out without interrupting in the product formation. So here, why we are doing this Monarch equation? So when you talk about a Monarch equation, this helps to determine the maximum specific growth rate of this based on a substrate utilization. So based on a time, how much amount of the organism has been utilized for the product formation can be plotted, and this has been shown in this figure. So here we are going to take this nu as a nu ms divided by Ks plus S, as we all know that this is a Monarch equation. And for your specific growth rate, this can be written as you all been aware, the dx by dt into 1 by x as the nu. So 1 by x into dx by dt as a nu, we are going to replace this new term in this Monarch equation. So finally we get as a dx by dt is equal to mu m into s into x divided by Ks plus S. So which means that it will not be able to describe your dead phase since your product is forming on a stationary phase after utilizing all the nutrients by the microorganisms for the product formation from the exponential growth phase. So the Monarch equation we do have as a nu is equal to nu m s divided by Ks plus S, in which we all the basic equation of a specific growth rate based on a microorganism, we can write the nu as your 1 by x into dx by dt. So just replacing this nu as 1 by x dx by dt in this Monarch equation, and finally we are getting what is the cell concentration that has been changed at a particular rate. So the nu n into s by s divided by Ks plus S. So here for your Monarch growth kinetics of an equation, we have two special cases. The first case, when your substrate concentration is more, in which we are going to make the substrate concentration is more, so that when compared to your Ks value, that is a specific substrate rate constant. So when your concentration is more, substrate concentration is more, the Monarch equation of this equation dx by dt is equal to mu s by into s divided by Ks plus S will become, so which means that yeah, S is said to be a more when compared to the X, so that this Ks will be equivalent to 0. That means that the Ks term is said to be the negligible one. That is a one special case. So at higher substrate concentration, the S is more than the Ks. So the Ks value is said to be the negligible one. So what happens if it becomes 0? The dx by dt is equal to, it becomes as mu m into s into x divided by s. As your this Ks has been negligible one. So when we are talking about the dx by dt will finally become as a mu m into x. So whatever the specific growth rate we do have, that is directly proportional to the cell mass concentration. Okay, so this is a one special case at your high substrate concentration, the Ks will be of a negligible part. So the growth rate, whatever it has been occurred, that growth we are going to take it as a maximal growth rate, that is the nu max. And the second case is the substrate concentration is very less when compared to the specific substrate rate. So here, how the Monarch equation will become? In this equation, you substitute the dx by dt is equal to mu max s into x divided by k plus s. So here in this case, your substrate is less when compared to the k. So the s term will be becoming 0 in this denominator. So finally, it gives you in the case when the low concentration of a substrate, the dx by dt is equal to mu max s into x divided by ks. So this represents your whatever the cell mass it has been produced, it's entirely based on a substrate concentration, which follows your first order of a kinetics. So the growth rate is a very sensitive to the substrate concentration, which means that the growth rate is directly proportional to the substrate, so that it evolved in a biomass concentration in the terms of your x. So the next one. So what are the why we are studying this Monarch equation? Why we are relating the Monarch equation with the microscopy and kinetics? And this why it plays a major role in the case of a bioprocess engineering is that it is aims to produce all the product that has been produced by the fermentation technology, which is utilizing the microorganism, in which it can be utilized your substrate for a product. So we are producing n number of your products day by day for in a larger quantity for our commercialized purpose, because for our utilization. So this can be related with the what are the various products that can be related. So here the first one is the primary metabolite, the second one is the secondary metabolite. So when we talk about the primary metabolite, it includes your, it will be related to the microbial cells in the growth phase, that is in your stationary phase. So what are the products that can be produced, like your alcohols, amino acids, your vitamins, your enzymes, which will come under a category of a primary or products or a metabolites. That is, the metabolite is due to the action of a microorganism, the product has been formed. The second is said to be the secondary metabolite. So when you talk about a secondary metabolites, it does not involve direct on a growth phase. There will be accumulation of a byproduct with the desired one. So that will be a product, that is, which means that there will be a formation of a toxic product along with the octo product. So here in this case, the secondary metabolites, we can have an example of an antibiotic and a toxin, which means that it does not have any relationship to synthesize your growth or utilizing your cell biomass. So when we talk about a microbial product that can be classified, so we have seen what are the primary metabolites and a secondary metabolite as a product, how it can be classified. So this can be classified based on 3 different types of a product. So when it is been based on growth of a microorganism, it occurs during your stationary phase. When the growth of your organism occurs, it will be involved in the formation of the product. So we call that product as a growth associated product, which means that it is defined as a product that are produced simultaneously when your microorganism has been growing. So the specific growth rate of a product formation is directly proportional to the specific growth rate of the microorganism. So the growth is directly related to your product formation. So the specific growth rate of a product is directly proportional to the specific rate of the microorganism growth. So here, as your product concentration increases, your cell concentration is also increases, which means that the cell is getting increased so that the product has been formed, directly proportional. The next type of a product is a non-associated. So here in this case of a non-associated one, when you talk about a non-associated product, a non-growth associated product, the growth will not be involved directly for a product formation. So this can be depicted in this figure. So this is said to be the growth associated product. As your product has been formed, the cell mass has been increases, or we can directly relate it with your, as the cell mass has been increased, so it results in a product formation, directly influences. When we talk about a non-growth associated, the product will be formed whenever it does not involve in a biomass concentration, which means that it is not directly related. So here that's said to be the non-growth associated products. Okay, so which means that the specific rate of a product formation is not directly proportional to the specific growth rate of a microorganism. So that can be written as your QP is equal to beta. Okay, that is said to be the specific growth rate or a product rate, that is the QP is said to be the constant, that is the beta, which means that it is not directly proportional to the growth rate of a microorganic cells. Okay, so the next third product is said to be the mixed growth associated product. So what is the mixed growth associated product? In the sense, as your product is being there, that is directly proportional, that is, which means that the product has been formed based on a cell mass concentration, in which the addition of your product has been formed without your, that is independent of your biomass concentration. That addition we call it as a mixed growth associated product. So it is half of the way which will be acting as a growth, half of the way it will be acting as a non growth associated. So the mixed growth associated is said to be the product formation of a microorganism from the microorganism is dependent on both the growth and a non-growth associated, which means that it takes place during the stationary phase along with the combination of your whatever the desired product we do have, that will be involved in the formation also as a byproduct or an undesired product. So it is said to be the combination of your growth associated as well as the non-growth associated. So here the specific product formation rate QP can be written as alpha nu plus beta. So the alpha nu is said to be here, which is said to be the growth associated specific product formation, and beta represents the specific growth associated on a non-growth associated product, which is not directly proportional to your cell mass concentration. So the QP is equal to, it is a mixture of your growth associated as well as the non-growth associated. So the alpha nu plus beta is equal to the specific product of your QP. So from this equation, we can say this equation is said to be the Lute-King-Piret equation. We call this equation as a Lute-King-Piret equation, which is used to determine the product formation rate. QP is equivalent to your alpha nu, that is based on your growth associated as well as the non-growth associated product. So why we use this Monarch model for your product formation? So this gives you the mathematical model. This can be used as a mathematical model for any fermentation product that has been formed during the fermentation process. So which is used to improve the batch performance. That is the batch process, how it is being carried out, or if it is of a continuous, how the performance is being carried out. So that gives you the kinetics value. So whether this follows a first order or a second order kinetics, that can be determined. So when we talk about a Monarch, when we are having a second case as when your substrate concentration is very, very less when compared to the specific rate, substrate rate, in which the substrate rate is lesser. So it is said to be the negligible one. So which means that your dx by dt is equal to nu max s into x divided by ks value becomes, right? So with this follows your first order kinetics. So it is used to determine whether it follows a first order or a second order kinetics. So it is used to solve any problem that has been encountered in a fermentation process. So whatever the product has been yielded by utilizing the substrate, which makes your productivity increases, which makes the product to be in a higher case, so that whether it can be used to determine whether it is of a first order kinetics or a second order